Hello everyone and welcome to the video on graphing sine and cosine. In this video, as I was working on this one, it became very evident that there are some things that I feel can work with what I've been doing this year, and some things that can't. And so this video really is going to focus more on some of the definitions that we have and some of the things that you're going to have to find. So we're going to continue with this video, but we will do most of the lecture on actually graphing the sine and cosine functions and what I'm going to expect to see in your graphs. That will be done in class. So in order to go and minimize the amount of time that I would have to do that, I am going to continue with this, and you will need to focus on the definitions and the basics in terms of what a sine and cosine function looks like. So our objectives for this one, again, to recognize the graph of the sine and cosine functions. Number 2 is determine the amplitude and period of the sinusoidal functions. And the third thing is determine what's called the phase shift of the sinusoidal functions. Sinusoidal functions are just anything that looks like sine and cosine, like a sine function that has that repetitive nature. Our conceptual objectives on this one are: 1, understand why the graphs of sine and cosine function are called sinusoidal. Kind of just mentioned that because of how they look. And the second thing is understand the cyclic nature of periodic functions. Now, what does it mean when we talk about a periodic function? Well, a lot of things that we deal with out in the real world, per se, have a roughly periodic, in that they don't repeat exactly, but they do have a repetitive pattern that we can use to predict things. So anything that does repeat itself in a predictable way would be considered a periodic function. So things like heartbeat. If you take a look at when they do the the EKG, I think, when they do an EKG, if you look at that, you can see a repetitive pattern happening there. The other thing, you have tides, the high and low tides that we have. Those are repetitive because the tide comes in and out, and even the amount of the tide, how high it comes up, how high the high tides are, and how low the low tides are. That is also a periodic function. Another thing that we have is the amount of daylight. Right now, we are in where daylight is very short. The amount of daylight that we have during the day is very short, and we have much, so that's why it's getting light in around 7, almost 8 o'clock, and it's getting dark at 5:30, 5:40, somewhere around there. During the summer, that's almost switched. It's getting light at 5 a.m. and it's getting dark at 9:30, 10. And so the amount of that daylight that we have adjusts as well. And the same thing, other things we have, the average temperature. If you take a look at the average temperature that we have throughout the year is a periodic function. It raises up and drops down, and it makes sense that would happen because of the nature of a year. Okay. Definition: a function is said to be a periodic function when there is a number p such that f of x plus p equals f of x for all x in the domain of f. In other words, this is a graph that can be shifted down left or right a certain amount, and the graph would then fall right. It would start to fall right back on itself. Okay, if p is the smallest such number for what this holds, then p is said to be the fundamental period, or often we just call that the period. Now, the one thing to remember are trig functions. Because if they're defined on that circle, they're also called circular functions. They are all periodic functions. And so what we find, remember when we talked about with the unit circle, how if we go one time around, every angle coterminal to an angle on the unit circle is going to have the same sine and cosine values. Well, sine and cosine have that periodic nature, and so I know that anytime I add a multiple of 2 pi to theta, I'm going to get the same thing as the sine of theta. And the same thing with cosine. So if I shift that graph a multiple of 2 pi left or right, I am going to go graphically, the sine function, the sine of theta plus 2n pi, and the graph of sine of theta would look exactly alike. You couldn't tell the difference between them. And this is true as long as n is an integer. Now, the fundamental period of both of these functions, because the smallest that it could happen would be when n is 1, our fundamental period, and for both of these, is equal to 2 pi. So that is the fundamental period that we work with sine and cosine functions. Now let's look at the graph of the sine. We'll start with the sine curve and then we'll look at the cosine curve. What we see over here is a table of values. Now I've just pulled out the values, the values for 0, pi over 4, pi over 2, 3 pi over 4. We're just moving up by pi over 4 radians every time till we get to 2 pi. And then over here you see the sine of each one of these angles. The sine of 0 is 0. The sine of pi over 4 is square root 2 over 2. Sine of pi over 2 is 1. Sine of 3 pi over 4 is square root 2 over 2. Sine of pi is 0. When we put 5 pi over 4 in there, the sine of 5 pi over 4 is negative square root 2 over 2. Sine of 3 pi over 2 is negative 1. Sine of 7 pi over 4 is negative square root 2 over 2. And the sine of 2 pi is back to 0. So plotting the points, which is what you see the author has done here, plotted the points, we get this sine curve. Now, you have to remember here that, again, these points repeat. So if I went another pi over from here, if I went another pi over 4 units, I'm going to be up at square root 2 over 2. If I go another pi over 4 units after that, I'll be at up at 1, and it will just continue this pattern. So graphically, what you see down here is really two complete periods of the sine function. The first period, what we see graphed here, is this portion right here, and then we've worked that same pattern going back in the other direction. Now, the thing to remember with the sine curve, the domain of the sine curve is negative infinity to infinity. Therefore, you know that there will never be any vertical asymptotes in a sine function. It will just have this wave pattern that you see here. It will just do that wave going up to 1, down to negative 1, and back and forth like that. That will continue on forever. The range is going to be from negative 1 to 1, which you can see from the graph. It is an odd function. Remember, because it's an odd function, you can think of it as some people will think of it as a double flip, others a rotation. It is symmetric about the origin. So if I take this particular high point right there, if I flip that over the y-axis, I'm going to be here, and then when I flip it over the x, it comes down here. This low point, when I flip that over the y-axis, it's coming over here, and then above over the x-axis, it would be up here. Okay, so this is an odd function, and again, the period of this function is 2 pi. Now let's look at the cosine function. And again, we did the exact same thing with that you saw in the last slide. With the sine curve, we have our x values, which we picked as being the every pi over 4 units from 0 to 2 pi. And then right here you see the values of the cosine of each one of these angles. And so when we look at that, when we graph it, 0, 1, so we put the dot at 0, 1, so it's up at a high point. Now notice here one of the differences you have to recognize between the sine and cosine, because graphically they are going to look very similar. Is where this thing is at 0. Okay, right now we're going to call that's where this thing starts. In this case, the cosine function is up at a high point. If you look at the sine function, it was starting when we put 0 in, we were right at the origin, and it was right in the middle. So in this case with cosine, it's at a high point, and then we just plotted the points along, and we got this portion of the graph of the cosine function. That would be one cycle of that graph. Now, the amount of time here, the length of time, this would represents the period. The actual shape that repeats is called the cycle. And you can see down below again, I've done another complete period over onto to the left. And so you can see that the wave nature, and that should look pretty similar to what you saw in the graph of the sine function. And again, like the sine function, the domain here is from negative infinity to infinity. The range is -1 to 1. This is an even function. An even function, remember, is a reflection over the y-axis. And I think if you look at this graph, you can see that nature of that reflection. And again, the basic period of our cosine function is 2 pi. Now, as we've mentioned, you've heard the term sinusoidal a few times. These graphs are examples of sinusoidal graphs, which means that it is resembling the sine function. Okay, so cosine function is a curve that resembles a sine function. The sine function obviously resembles itself. But the thing that you have to remember on this is that we can resemble the sine function by doing other types of transformations. So when we look at these, any function that has that form of y equals sine x or y equals cosine x is going to be a sinusoidal function. Now, there could be transformations. These sinusoidal functions are subject to all the same transformations we worked on in Chapter 1. So to start out with, let's just take a look at these two. We have y equals a sine of bx and y equals a cosine of bx. And it doesn't matter which trig function I have in there. The value of a, you have to recognize that is outside. It's multiplying the function. It's outside the function. So I know when we're outside, it is going to be a vertical stretch or shrink of that curve. With the value of b, that is inside the function. So that is going to be a horizontal stretch or shrink of that curve. Now remember, the other thing you have to remember is that these things had a factor. In this case, for the vertical stretch, it's by a factor of a. And with the horizontal, it's by a factor of 1 over b. Remember the relationship that we had there. That inside, when it's outside, it does what we expect. When it's inside, it does the opposite. So now let's take a look at the amplitude. The amplitude of a periodic function is half the distance between the maximum value and the minimum value. So when we do a vertical stretch or shrink, it is going to change the amplitude of that function. And it's also thus going to change the range. When we looked at y equals sine x, that one went, the highest value, its maximum value was 1. Its minimum value was -1. So the distance, if I take the distance from 1 to -1 is 2, and the amplitude is going to be half of that. So the amplitude was 1. And so in this case, the range on that sine function we know was -1 to 1. Now when I do the 3 sine of x, that means what's going to happen is that I am going to go and stretch this thing by a factor of 3. So my lowest values, instead of going at -1, my lowest values are going to be pulled 3 times farther away below the x-axis. So it's going to be to -3. And the highest values are going to go to 3. So this 3 sine of x is going to go between -3 and 3. And in this case, the amplitude is equal to half the distance between my highest and lowest values. Well, my highest value is 3. My lowest value is -3. And so the distance between these two is going to be 6. And thus the amplitude comes out to equal 3. In this next one, my values here, we have a vertical shrink by a factor of 1/2. So in this case, instead of going from -1 to 1, it's going to go from -1/2 to +1/2. Make sure that's negative there. And the amplitude that we're going to have is equal to 1/2. When I have a -4 sine of x, that's going to be now the negative is a reflection, so I don't have to necessarily worry about that. But the 4 is going to be a vertical stretch. So in this case, it's going to go from -4 to 4 is going to be the range, and the amplitude is going to be 4. Okay, so right now I'm hoping that you recognize a pattern that is happening here in terms of identifying the amplitude when you look at that function. The next thing we have is the period. The period is really the amount of time, the horizontal distance it takes for the sinusoidal function or a periodic function to repeat itself. Now, and really when we stretch or shrink this sinusoidal function horizontally, we're going to change the period of that function. So when we look at cosine, we'll deal with cosine here, but it's the same for sine. We know the period for cosine is equal to 2 pi. So when I look at this, remember when we look at the transformation, that 2 right there, that is a horizontal shrink by a factor of 1/2. Well, when we are shrinking every point's distance away from remember, the y-axis by 1/2, that transformation, that amount of that horizontal stretch or shrink is also going to be applied to the period. So in this case, my period on this problem is going to be, it will come out to be 1/2, I would have 1/2 times the 2 pi, which would be pi units. So in this case, the period comes out to be pi. In this next one, b is 1/4. That is a horizontal stretch by a factor of 4. So in this case, it's going to be, the period is going to also be stretched by a factor of 4. So it's going to come out to be 4 times 2 pi, which comes out to be 8 pi. And that will give you the period of these sinusoidal functions. Now we're going to add in a couple other transformations here. We know we're going to take this as a sine of bx plus c plus the d. So we're adding the c and the d in there in both of these. Now in this case, the c indicates that there's going to be some sort of horizontal shift, either left or right. And the d is going to indicate that there is a vertical shift, either up or down. And so the amount of that shift is going to be important to us in terms of identifying how to graph these functions. When we talk about the horizontal shift of these functions, it is going to be, it's also called the phase shift. So most of the time when we talk about this for our graphs of sine or cosine, we're going to be talking about a phase shift. And you need to remember that that does represent the horizontal shift. Now the other issue we have with this is that when we do these problems, a change in the period is also going to affect the amount of the shift, of the horizontal shift that took place. Now the one thing that you have to keep in mind, when we worked with something like this one right here, this one we recognized that was a +3 inside, and we would have said that would be a horizontal shift to the left 3. And so because it's a sinusoidal, we're going to call it a phase shift, and it is to the left 3. And that would be correct. That would be correct. Now the important thing that we have here to identify the phase shift, we want the coefficient on the x to be 1. So in these right here, that's not the case. So we're going to go and modify it so that we can identify that horizontal shift. In this second one right here, what I know is I can go through on this, and I'm going to go and pull out a factor of 2 from what's inside. So what I'm going to have then is I'll have y equals the cosine of 2 times, well, that's going to be x, and by pulling out a factor of 2 from that 3, it's going to be plus 3 over 2. And so in this case, there is a phase shift, and the amount of phase shift now is that value there. So in this case, the phase shift on this for this particular problem comes out to be that it is going to be to the left 3 over 2 units. When we look at this third one, when I need to pull out a factor of 1/2, well, when I pull out a factor of 1/2, that's going to be like multiplying this by 2. So what I'm going to have when I do this, I will have y equals the cosine of 1/2 times x plus 6. You can check both of these here by distributing the 2 or distributing the 1/2 and showing that you do get back to what we started with. But because I've pulled out that, I can now identify that my phase shift in this case is just going to be that particular value. So for this problem here, the phase shift is really going to be to the left 6 units. To summarize these, and these are things that you're going to be asked to identify every time you do a graph of a sine or cosine function. You're going to be asked to identify the amplitude, the period, the phase shift, and the vertical shift that takes place as well. In this case, the amplitude, what you should have noticed on that is that amplitude always, when we looked at those problems before, the amplitude was always just the number that was in front of the sine or cosine function. Well, because that number could also be negative, we tend to use the amplitude as the absolute value of A. In this case, the period. Period will always be 2 pi divided by b, whatever b is. The phase shift is always, when I pull that b, the period out, the b out from this, I am going to end up with a c over b. So the phase shift in this case is always going to be minus c over b. And the vertical shift is going to be whatever d is. These are the values that you're going to be working with as in terms of graphing. Now, there's a lot more that goes into graphing these functions. We are going to be how we go, where we have to identify where things start, where they're going to end, and how to go and scale our graphs, because our graphs are going to have to be accurate. So a lot of what we do, you have the terminology right now with this. You need to make sure that you are comfortable with it and you know all of these right here, and you know that the basic look right now of a sine curve and a cosine curve, specifically where that, in terms of, if you look back in on the notes, in terms of when I actually plotted where we had the plotted out pointed, the graph with the plotted points, where that sine curve and where that cosine curve started, because that will also be a key on this. So with that, I hope that you are feeling okay with this right now. There is going to be a lot of stuff that we're going to be doing in class next time. So with that, I will say goodnight and say see you in our next class.